All right, welcome back. So let's talk about a new way of creating a proposition from old propositions, and this is called a conditional statement. And we write it like this: P arrow Q, and we translate this to the proposition if P, then Q. And so let's pick on our favorite propositions. P can be the proposition it is sunny, Q can be the proposition I go for a run. P arrow Q is simply the new proposition which says if it is sunny, then I go for a run. Nothing too startling going on there. And we can write this other ways. We could say if P, comma Q. So if it is sunny, then I go for a run. Sometimes in English we would just say if it is sunny, comma, I go for a run. We could say P is sufficient for Q. It's being sunny is sufficient for me to go for a run. We could say Q, if P, I go for a run if it is sunny, and so on and so forth. And you can read some of these equivalences in the book. We can talk about them in class. But English is a tricky language. Spoken languages, written languages are inherently filled with imprecision. And propositional logic is trying to be very precise. So when we write this, we know exactly what it means, if P then Q. When we write something like a necessary condition for P is Q, or P only if Q, it can start to get confusing. Okay, so we'll mostly stick to this idea of if P then Q, and P and Q are just the declarative statements that those propositional variables represent. So as with conjunction and disjunction, we'd like to represent a truth table to show us exactly what this conditional does. So again, P and Q have 4 possible combinations of truth values. And for each one, we can list what the conditional if P then Q is. Well, if P turns out to be true and Q turns out to be true, there's certainly no argument that this statement, if P then Q, is itself true. And if P is true and it turns out Q is false, P is true and Q is false, then this statement, if P then Q, is absolutely false. This claims if P is true, Q is true, but if it turns out P is true and Q is false, that conditional is false. So those 2 rows of the truth table are pretty intuitive. These top 2 rows are very non-intuitive. Suppose P turns out to be false, but Q turns out to be true. Would we claim that this conditional statement is now false? Probably not. So let's look at this. Suppose we say, if it is sunny, then I go for a run. And I'm going to tell you that that's true. Okay? Anytime it's sunny, I'm out there for a run. Okay? The sun comes out right now, I'm going to go out for a run. Suppose you wake up and it's cloudy. Is this statement invalidated somehow? Suppose I'm out running and it's raining. Does that somehow invalidate the statement, if it is sunny, then I go for a run? No. We're not claiming that if I go for a run, it's sunny. We're claiming that if it's sunny, I go for a run. Well, it's cloudy and I'm going for a run. That's okay. This conditional statement might very well still be true. And in this first row, say it's cloudy and I'm sleeping in. Have we invalidated this conditional that says if it's sunny I go for a run? We have not. Now these upper 2 cases, they feel kind of weird, okay, usually. So let me give you a different pair of propositions that may make this a little more palatable. So let P be the proposition x is bigger than 1,000, and let Q be the proposition x is bigger than 10. Okay, suppose I set x equal to 1,000,000. X is bigger than 1,000 and x is bigger than 10. So P is true and Q is true. What does P arrow Q say? P arrow Q is a proposition which says if x is bigger than 1,000, then x is bigger than 10. Do we believe this? Suppose x is an integer, right? If you pick an integer that's bigger than 1,000, is that integer bigger than 10? And I think you have to agree that this is absolutely true. Any number that's bigger than 1,000 is bigger than 10. We know that. That's the way integers work. So if we set x equal to 1,000,000, yeah, it's bigger than 1,000, it's bigger than 10. P arrow Q should definitely be true. Now what about the second row up here? Suppose x is equal to 50. Well, is x bigger than 1,000? No, 50 is not bigger than 1,000, so P is false. But x 50 is bigger than 10, so Q is true. So if x equals 50, we're in the second row here where P is false and Q is true. Does this statement suddenly become false just because I picked a value of x where P was false? No, this statement is absolutely true. If x is bigger than 1,000, it's bigger than 10. So this has got to be true, and this is an example of the second row of this truth table. Now suppose I pick x equal to 0. Is x bigger than 1,000? No. Is x bigger than 10? No. P and Q are both false. But just because I picked an x equal to 0 does not suddenly make this very, very clearly logically true statement become false. If x was bigger than 1,000, it would be bigger than 10. I picked an x that wasn't bigger than 1,000. But that doesn't change the validity of this statement. This statement is still absolutely true. Now what's missing in our analysis is this third row. And I cannot find a value of x where P is true and Q is false. But if I could, if there was some new integer that was created tomorrow, and that integer was bigger than 1,000, but was not bigger than 10, then P would be true and Q would be false, and suddenly we would have an example where this conditional was incorrect, where this magic value of x satisfied the fact that x was bigger than 1,000, but it failed to satisfy x is bigger than 10. And in that case, this conditional would be false. But there is no such x. So this is the valid truth table for a conditional statement. And we'll have to kind of live with that for now, but it'll become more clear as we work with it, I think, why this truth table makes sense. All right, so terminology, when we say P arrow Q, P is called the hypothesis, and Q is called the conclusion. All right, there's also a biconditional, which is basically if P then Q, and if Q then P. And this comes up a lot, so frequently that we have a special notation for it, which is just P and a double-headed arrow and then Q. And when we see this, we should interpret it as if P then Q and if Q then P, so it's two arrows going opposite directions. So that's pretty straightforward. And the truth table for this, if we were to spell it out, it turns out that we have an extra false here in the middle. But the biconditional is true if P and Q are both false or P and Q are both true. So we can think of this as P if and only if Q. And we have a shorthand for if and only if because that pops up a lot. It's an if with two F's. So P if and only if Q is the same as the biconditional. All right, the last thing we want to talk about in this lecture is three other ways of creating new propositions from old. So suppose we have P and Q being two propositions, and we have our conditional proposition if P then Q. Well, we can create a new proposition called the converse. And the converse of this basically says if Q, then P. If I go for a run, then it's sunny. The inverse says if not P, then not Q. And the contrapositive says if not Q, then not P. And again, let's think about P, it is sunny. Q, I go for a run. So this conditional says, if it is sunny, I go for a run. Okay, fix that in your mind. If it's sunny, I go for a run. Anytime the sun's out, that's it, I'm outside, I'm running. Okay, what does the converse say? If I go for a run, it is sunny. That's clearly a different statement, because you know what? I might run all the time. I might be out there running 24/7, whether it's sunny, whether it's rainy, whether it's snowing. This statement is saying if I go for a run, then it is sunny. And that's not necessarily true. It's not necessarily the same as this, which says if it's sunny, I go for a run. Because maybe I run every single day, in which case this is certainly true. If it's sunny, I go for a run. But you know, if it's cloudy, I might go for a run. So we can't say if I'm going for a run, then it must be sunny. So this is not the same as P or OQ. And the inverse says if it's not sunny, then I do not go for a run. And that's a different statement. But the contrapositive says if I do not go for a run, then it is not sunny. And that turns out to be logically equivalent to the original conditional. So we can write this equal sign with 3 bars. And this is logically equivalent. If you were to write the truth table for this, and write the truth table for this, they would have exactly the same truth values in every single row. That's what logical equivalence means. But this we can say is not logically equivalent to if P then Q, and this is not logically equivalent to if P then Q. So we'll play around with these in some homework problems. We'll look at propositions that are conditional, and we'll look at converse, inverse, and contrapositive. And the equality of the contrapositive to the original conditional is going to be a key to how we can do proofs by contradiction. And the failure of these to be logically equivalent to the original conditional is going to lead to our analysis of what are called fallacies, statements that are not logically correct. And fallacies are very important to understand. All right, so that's it for this lecture.